we've all been waiting for, and you get to dust off that linear algebra and put it to good use. So you knew it was going to pay off, all your hard work, and here we go. We're about to use it. So we've developed different solution techniques for input-output ODEs. So if we have our system representation in input-output ODE form, then we know how to solve it. We've used the method of undetermined coefficients. We've used that along with superposition and the differentiation property. Those two properties apply to linear time-invariant systems, LTI systems. And we also have added these first and second order system response tables to our repertoire. I mean, seeing how the system, how the first and second order system responds to these different types of inputs and to initial conditions was one of the motivations we had in the last chapter. But also, we wanted to learn how to how to construct solutions to very common systems, first and second order systems, without going through and rederiving the solutions from scratch every time. So that's why we developed the tables with the, along with those properties that we could use to construct many different types of solutions for many different types of problems. And that's very powerful. And that's like the kind of the extent of input-output ODE solution techniques that we're going to go into. We will mention, I suppose, I guess I shouldn't say that, because we will mention more in passing than anything else how to do it with Laplace and Fourier transforms. In a few weeks, we'll get there. But that's not a focus of how we're going to solve them in this class. It's totally fine if you use Laplace and Fourier to solve them, but that's just not the focus that I'm going with. Although it could be. That would be totally legit, totally fine. So, but one of the other forms of the system model that we've learned how to construct is the state space model. Okay, and that state space model, thus far we've played a little bit, we've dabbled a little bit with simulating in MATLAB, the state space models that we've developed, but we haven't learned how to actually deal with them directly, how to solve those state space models. Remember, those state space models are differential equation models, and we haven't learned how to do a solution directly on those. So that's what we're going to learn in this chapter. That's the main thrust of this chapter, is to construct solutions to state space models directly. So it's totally doable and fun in many cases, for linear systems at least. So recall that for a state space model, the state x, input u, and output y vectors, or actually vector valued functions, interact through two equations. So the state equation, which has the time derivative of the state variable vector, so dx dt on the left-hand side, and then some function of the state variables, the inputs, and then sometimes explicitly time. If it's a time-varying system, time can show up explicitly in the right-hand side of this state equation. And then the output equation, which is just an algebraic equation that is a function of the state variables, the input variables, and potentially time as well, explicitly. So together they comprise what's called the state space model of a system. So this is a familiar object to us. In accordance with the definition of a state-determined system, given an initial condition and the input, the state x is determined for all time. Determining the state response requires the solution, analytic or numerical, of the vector differential equation 7.1a. So you need to figure out what x is, so you need to solve this vector differential equation. The second equation, 7.1b, so this output equation, is algebraic. It expresses how the output y can be constructed from the state x and input u. This means we must first solve the state equation for x, then the output y is given by 7.1b. So 7.1b is really just plug and chug algebraic equation. So once you have x, u is given, and time your solution will be a function of time, so that's fine. So once you have x, you know y from the 7.1b. So that one doesn't need to be solved per se. Just substitute x in, and you've got your solution. So just because we know that for a state-determined system there exists a solution to 7.1a, to the state equation, doesn't mean we know how to find it. Okay, so that's like, it's nice. Oh wow, state-determined system. We have a state equation. So there must be a solution, but that doesn't mean you know how to construct the solution. So in general, f and g, so the right-hand sides of these equations, can be nonlinear functions. We don't know how to solve most nonlinear state equations analytically. So that sucks if it's nonlinear. We don't know how to solve most nonlinear state equations. An additional complication can arise when, in addition to states and inputs, system parameters are themselves time varying, and this is when we have that explicit time argument that shows up in f and g. Fortunately, often a linear time-invariant model, or LTI model, is sufficient, and that's what we're going to focus on, the linear time-invariant model. So recall that an LTI state-space model is of the form, so this is our nice linear time-invariant expression of the state model. So dx dt equals some matrix A times the state vector x plus b times the input vector u, and the output is, again, an algebraic combination of the state and input vectors. So we learned how to derive these from linear graph models in Chapter 3, and so we've learned how to create these, and now we're going to learn how to solve them for the state response, and then substitute the result into the second equation. So we're going to solve 7.2a and substitute the result for x into 7.2b. So that's what our goal is here. First, we learn an analytic solution technique, and that's what we'll focus on in the first couple lectures. And then the last lecture in the chapter, I think it's 7.4. We'll learn simple software tools for numerical solution techniques. So we'll explore how to do this in MATLAB, and it's almost trivial. So the example I do in that lecture, I do a sort of hybrid of the analytic technique, and then I show a numerical solution as well. So we'll explore that, and that's pretty much Chapter 7. Okay. Any questions on like the broad goal of Chapter 7 here? Cool. All right. Let's do it then.